Okay, so without further ado, it gives me great pleasure to welcome the first speaker of the day to give the first TNQ talk of the week. I'd like to welcome Professor Mikhail Lyubich from Stony Brook. He's going to tell us about Julia sets, Kleinian groups, and Schwarz reflections, relations via David Sergiy.
Okay, thank you, and well, thanks to all the organizers for making this event happen. So it's my first time in India. It's very interesting. So very good atmosphere in this conference. Okay, so I would like to tell you some surveys, or to give you some survey on 4 themes of holomorphic dynamics unified in a very tight way together. Or rather, anti-holomorphic dynamics, and that is why I call it mirrors of conformal dynamics, because there will be all these reflections through various mirrors. And some of these themes are very classical and very familiar. It is just, well, anti-holomorphic maps, so Kleinian groups. In this case, it will be Kleinian reflection groups. And so we know through Fatou-Sullivan dictionaries that they're very closely related. But so there are some other features which are not so well explored, not so well understood. It is, well, understanding, unifying these themes through algebraic correspondences. So there was some work in this direction, but it is so barely, the work has barely started. And the fairly brand new theme, it is the dynamics of Schwarz reflections, which is also a very nice unifying, turns out to be a very nice unifying theme in holomorphic dynamics. And all this will be based on the work of 10 people, so not of them are listed here, but there will be more specific references. It's about a dozen of works, actually, though it started just about 7 years ago. And, well, there is a common denominator. So on all these works, it is Sabya, so who participated in all of them. So it is the only author who actually took part in all of these works. Okay, so it is a kind of recap of these features. So Fatou-Sullivan dictionary is a big theme in holomorphic dynamics, which kind of stimulated in the 80s, very much stimulated the whole field of research. And so it is always considered as some philosophical connection between the areas, which allows to pull back and forth various conjectures and ideas, structures. So, but it was really observed some explicit tight relation between objects. And here today, we will give you some really explicit relation between the two schemes. So somehow, really, so a way to transit, at least under some circumstances, from one object to from one part of the dictionary to another column of the dictionary. So, well, and a new, as I mentioned, a new theme is the dynamics of Schwarz reflections in quadrature domains. And so quadrature, these Schwarz reflections in quadrature domains is some topic which is it's kind of classical topics, quite familiar to analysts and mathematical physicists and just physicists. But there was not much dynamics there, but it was observed some time ago, maybe 10 years ago, by Makarov and his junior collaborator, Lee, that there is some dynamics involved, and the dynamics can be, in certain cases, usefully applied to some problems about quadrature domains. And so I visited Nick Makarov like about 7 years ago in Caltech, and he showed me some pictures they produced and some conjectures that were naturally suggested by these pictures. So, and it was very fascinating because it was clear that somehow something coming out from the Schwarz reflections, which looks very familiar for us. And so I came back to Stony Brook. Sabya was there, Samilna lecturer at that time. We started to discuss this, and so the field started to gradually develop, and many other people got involved. And so today I will update you on the current situation. And in particular, so one of the constructions which naturally come out of Schwarz reflection, it is the construction of matings between groups and maps. So groups and maps under certain circumstances can be mated, obtaining some hybrid object. And this hybrid object turns out to be interpreted sometimes as a Schwarz reflection on many occasions. And it can be done in a quite regular way. So this phenomenon, in principle, phenomenon of mating groups of maps, so was observed before. It was in the 90s. So it was discovered by Bullitt and Penrose, who somehow constructed some algebraic correspondence, which turned out to be, they show that it is a mating. Well, so at least conceptually, they show that it should be a mating of quadratic polynomials and the modular group. So the phenomenon was observed before, but in the holomorphic setting, it is a kind of more intricate to construct in a regular way such kind of matings. It turns out that anti-holomorphic setting has some substantial advantage, and one can just really produce these objects in a very systematic way. And in particular, it can be also done by David surgery. It will be some emphasis today. I will put some emphasis on David surgery as opposite to the quasi-conformal surgery, which is more special, which requires some more special situations to be applied. Those are such situations that I hope to mention. And again, the algebraic correspondences in this story also now arise very naturally from Schwarz reflections. So from certain Schwarz reflections, they can be lifted by polynomial maps or rational maps and produce algebraic correspondences in a natural way. So all this comes together in some very natural way. So, but I should say that in recent years, there has been some work by Sean Bullitt and Luna Lamanotti, who is here, in the holomorphic setting, who managed to confirm some of the Bullitt-Penrose conjectures. And so now we are trying together understand closer connection between holomorphic and anti-holomorphic. In the end of the day, maybe holomorphic setting can be developed as well as anti-holomorphic, though it is more subtle. So maybe Luna will tell you a little bit more on Wednesday, maybe not. Okay. So so what are quadrature domains and what are these Schwarz reflections? Yeah, by the way, so I already gave this talk a couple of times. Some people, not this particular talk, but on this topic, some people heard quite a bit of that. But in the previous talks, I tried to emphasize examples, some special families, some special examples. So just to understand what is really going on, we at this time we already accumulated sufficient amount of examples so that we feel comfortable to build up quite general theory. And maybe today there will be a bigger emphasis on some general constructions, general structure. But still, I will start with some example. But let me give a definition before going to this example. So what is Schwarz reflection? What is quadrature domain? So quadrature domain, for me, it will be simply connected. Quadrature domain would be sufficient. So some domain on the complex plane, such that the piecewise real analytic boundary for this domain, and there is a local analytic reflection, Schwarz reflection, around analytic boundary. But for the quadrature domain, the reflection should be extended to anti-meromorphic function on the whole domain. So that is somehow semi-local, semi-global object. So it is defined just as a standard Schwarz reflection near the boundary, and then it turns out that it is extendable as an anti-meromorphic function to the whole domain. Of course, the simplest example is just the disk, just the standard reflection. But the next example is a cardioid, where is the chalk? What chalk is here? Well, the standard cardioid, and people in dynamics know very well. Well, I can actually. So they can justify that it is a quadrature domain very easily, because in the simply connected case, so if the domain is simply connected, the condition to be quadrature domain is a very simple condition. Just take a Riemann mapping from this domain onto our simply connected, from the disk onto our simply connected domain, and this Riemann mapping should be extendable as a global rational mapping. So it is equivalent characterization of a quadrature domain in the simply connected case. Rational mapping. Riemann mapping is a restriction, is a univalent restriction of a rational mapping. And people in dynamics know very well univalent restrictions. So, well, univalent restrictions, so what, which produces a cardioid. So, and it is actually the cardioid of the Mandelbrot set. Anyway, so, but let me start not with the cardioid for my purposes, but let me start with this example, which is deltoid, which is called as classical deltoid, so which will be classically obtained as when you roll so two circles along some unit circle. And it turns out that the complement of this deltoid is a quadrature domain. So the complement, including infinity, the complement on the Riemann sphere. So we have a Schwarz reflection, we have some Schwarz reflection on this complement to the whole Riemann sphere. This Schwarz reflection is an anti-meromorphic function, but this its restriction, so its restriction to here, well, this map, so sorry, this map onto this domain where it is defined, so it does not have degree, well-defined degree, and actually the degree over the complement of the quadrature domain is equal to d plus 1, where d plus 1 is the degree of our rational map R, degree of R. No, it extends to, yes, and anti-meromorphic map into this domain, in this domain.
And what do you mean by anti-meromorphic?
So it is just meromorphic function of z bar.
But then the local Schwarz reflection itself is holomorphic, right?
So it is anti-holomorphic.
Say that again.
Anti-holomorphic. Locally it is, so it is holomorphic function of z bar. Anti means today, anti means holomorphic of z bar, f of z bar. Z bar example is z bar. So 1 over z bar is a Schwarz reflection in the unit disk. So take holomorphic function, take, that is what anti means today. But that is what anti means today. So what are the features here? So we have some reflection, and we can start to take pre-images of our quadrature, of our complement of the quadrature domain, deltoid itself. And so we will obtain 3 pre-images here. So degree over this deltoid is equal to 3. There will be 3 pre-images. So the degree over the complement of the deltoid will be 2. So then each of these triangles will have 2 more pre-images. Each next triangle will have 2 more pre-images, etc. And we will, when we take all these pre-images, we will obtain a tiling of certain domain which looks like a cauliflower. Let me show you the beautiful picture of this tiling. So that is what we obtain by taking all the pre-images of the deltoid by our Schwarz reflection. And on the complement of this cauliflower, the dynamics will be so degree 2 branch covering, so orientation reversal in degree 2 branch covering with a double fixed, with a fixed point, super attracted fixed point at infinity. So this picture starts to look quite familiar. So when we see such a picture, so what we immediately try to do is uniformize the interior of this cauliflower, uniformize the exterior of the cauliflower, and look what kind of a dynamics we will obtain here and there. And so the dynamics, so the tiling which we'll obtain on the unit disk looks exactly like a tiling, so tessellation which comes from the action of the triangle modular group. So it is very familiar tessellation here. And on the other case, the dynamics on the complement of the unit disk becomes just z bar squared. And there is a gluing map, between these two exterior and interior dynamical systems, glued map on the circle, which is closely related to so-called Minkowski number theoretic function. So the Minkowski function is a function which relates very tilings to dyadic tilings. And that is, roughly speaking, what happens. That's exactly what happens here up to degree 3 covering. Well, so it is, well, I should say, what does it mean? So here we have a map. So how this map is related to the corresponding triangle group. The relation is very simple. So it is a so-called Nielsen map of this Fuchsian group. So we have this fundamental triangle for our Fuchsian group, take the complementary components and take the reflections in these complementary components. And so what we will obtain is Nielsen, what we call the Nielsen map, acting on the well, on the part of the unit disk, but in particular on the unit circle. It becomes just degree 2 orientation reversing map. And our Minkowski function so conjugates this degree 2 map just to z bar squared. So what we will obtain here is a mating between this Nielsen map associated with triangle group and z bar squared. So okay, so that is this beautiful picture again. So the question, one of the first questions that we can ask, so somehow when we see this mating, the question is whether we can produce this mating intrinsically just by taking these two actions and gluing together them by certain map. And we know that under certain circumstances it can be done by means of quasi-conformal surgery. But in this case, quasi-conformal surgery is not appropriate regularity for the map because our Nielsen map, so associated with the modular group, has parabolic points, and z bar squared is hyperbolic map. So there is no way quasi-symmetrically conjugate so dynamics near parabolic point to the dynamics near the repelling point. So it turns out that much more relevant regularity is so-called David regularity. So for quasi-conformal maps, the dilatation of the map should be uniformly bounded. And for David maps, the tails of the dilatation should exponentially shrink, exponentially decay. So, and it is already classical David theorem that there is integrability theorem, like integrability for Beltrami differentials with bounded dilatation. There is also integrability theorem for this kind of David-Beltrami differentials. And it turns out that this surgery can be indeed performed by the David map. So this map, this gluing map, extends globally to a map with David regularity, and somehow our Schwarz reflection with respect to the complement of the deltoid is the mating becomes the mating of the Nielsen map of the triangular group and z bar squared in this way. So if we did not know that deltoids exist, if they were not discovered somehow in the 17th century, then that would be the right way to discover the deltoids, so by this kind of mating. Okay, so that is one of the features that is enlightened by the deltoid. And something that I will not maybe emphasize too much today, but one can produce out of these dynamics, one can produce also some algebraic correspondence. And what one can do is to take this uniformizing map to the complement of the deltoid, which is this explicit rational map, and to take the deck transformations of these uniformizing maps, local deck transformations, and also reflection with respect to the circle. And this will be some algebraic correspondence, which will be in some way the lift of this Schwarz reflection. And so this algebraic correspondence can be considered as the mating of the triangular modular group and the map z bar squared. So it is a kind of phenomenon of the type discovered by Burrit and Penrose, but you see that here it is very simple and explicit example of this kind of phenomenon. And so that is kind of pictures which we obtain after lifting the Schwarz dynamics onto the algebraic correspondence. Okay, so I will not talk much about algebraic correspondences today, so I will keep it in mind. Okay, so what I would like to emphasize today is the David surgery, how David surgery can produce examples, whereas other examples of the matings between groups of maps. So let me formulate some general result that we proved in this direction. Yeah, by the way, so that is exactly so. So what is wonderful about the deltoid is that essentially all the features that we will discuss today already appear in this deltoid situation. So there is a mating performed by David surgery. This mating can be sometimes lifted algebraic correspondences, and the mating itself is a Schwarz reflection, etc. So just to understand this example, and then you can move further to much more general situations. So we developed some general theory for David surgery, some general technology for the David surgery. The situation is like that. So it is about conjugacies between some expanding maps, expansive maps, I should say, of the circle. So let us have the expansive degree D map on the circle here, expansive degree D map here. Let these maps be piecewise real analytic. So this is the domains of real analyticity here and there. So it can be orientation preserving or orientation reserving expansive maps. But it is not necessarily expanding maps. They may have parabolic points somehow. The maps are not necessarily exponentially expanding. So, but two such maps are always homeomorphic, and the question, what would be the regularity of this homeomorphism? So if the parabolic points match, so parabolic points go to parabolic points, then the regularity will be just quasi-symmetry, and this map would be extendable to a quasi-conformal map. However, if they don't match, it cannot be quasi-symmetric map, so it cannot be extended to quasi-conformal map. And that is exactly the situation when we try to make groups and maps. And so, but it turns out that under quite general conditions, it will be a map which is extendable as a David map. Namely, if hyperbolic points, repelling points go to parabolic points, then there is a David extension. So the inverse map will not be David map. Parabolics are not allowed to go to hyperbolic points, but if the hyperbolic points, hyperbolic dynamics can be turned to parabolic dynamics by David maps. That is the idea. It turns out that it is indeed true in this context of the circle expansive. Let me mention here that, like, for the mating theory, for the conformal mating theory, the Alfers-Berling extension theory is the key. So as a condition that the gluing map should have bounded ratio distortion. And in this case, in the David setting, of course, the distortion will not be bounded, but there is a condition given by Chen He and Zaheri, which tells us that if we go to a dyadic scale n, if the distortion is big of n in this scale, then there is a David extension of such a map. And we will use this criterion to show that so under our circumstances, and when hyperbolic points go to parabolic, then the condition of Chen He and Zaheri is indeed satisfied. So the map so the map admits David extension, so it can be basis for performing the David surgery. And there are various applications of this technology. So we can take a hyperbolic map and we can try to turn into parabolic map. It is actually already quite classical. It was this kind of examples were given in the Hasinski thesis. Hasinski was DOD student. So, and he gave such examples, and with different technology. He did not use the circle maps, but just local analysis near parabolic points. So we can take a hyperbolic map and we can turn it to the Kiss and reflection Kleinian groups, and I will give you examples soon. And we can also so then take a hyperbolic map and perform it to Schwarz reflection, and we can also do matings between maps and groups, as I already emphasized several times. And so using this this kind of technology. Also, so examples of mappings were known before by Bullitt and Hasinski, who showed that under certain circumstances, quadratic polynomials can be mated with the triangle, with the modular group as well. They had this kind of examples also. So just based not on the circle dynamics, but based on the Hasinski technology. Okay, so that is what we can try to do with our David technology. And so let me give you some examples how when this kind of technology can actually be applied. Okay. Well, so the first example, it is this Minkowski function, actually. So the fact that I already stated that the Minkowski function is the David function. If we go from the hyperbolic part plane to the parabolic, from the map to the group, then it will be a David map, and it is just application of our result. And one can think topologically, well, geometrically. So what is going on here? So that is kind of picture for z bar squared. And so what we are doing, we are blowing up the origin. We are blowing up the origin, replaces this tripod by the hyperbolic triangle, and built up a dynamics, so generated by reflections on the part, on the residual part, on the complement of this pole of this triangle. So that is what we how we can understand the surgery between z bar squared, the Minkowski map, which gives the conjugacy between z bar squared and the Nielsen map of the triangle group. And now this can be applied in many other situations on some invariant domains of the actions of Kleinian groups and rational maps. So there is a general idea essentially which will be applied all along to essentially all the examples that I will show you in this talk. Okay, the first example that I would like to take a look at, it is an Apollonian gasket, classical example. We have reflections in 4 circles. So that is 4 circles, and that is the picture of the limit set. We see here so invariant domains, well, some domains of the complement of the limit set, and we see that the action on these domains is actually triangular action. So there is a temptation, a clear temptation, so to take this triangular group and replace it with z bar squared, and so to try to see what we will obtain in this situation. It turns out that we can actually do it. So we can do this kind of replacement of that. So do this surgery. So this surgery acts now in the opposite direction. It looks that we are doing this in the wrong direction. So because we start with the group and go to the map z bar squared. So we go from parabolic to hyperbolic situation. But so still, if we will do this replacement of the group with the map, then we will obtain some anti-rational map of degree, or well, topologically we will obtain anti-rational map of degree 3. So topologically, but we know, so from the we know that under certain circumstances there is a way to realize this topological map as a geometric map, as an actual rational function. And it turns out that in this case it can be done. So there is a certain criterion which can be checked in this situation, and one can construct a rational map which will be post-critically fixed rational map, so hyperbolic post-critical fixed rational map, such that the dynamics on the Julia set of this map will be equivalently homeomorphic. The dynamics will be in some way conjugate to the dynamics of the group. So namely, so the dynamics of our rational map will be conjugate to the dynamics of the natural Nielsen map associated to this Apollonian group. So here is the picture. Here is the picture of the Julia set of this rational map. So you see, so it is what is called Apollonian rational map. Now you see that it is now hyperbolic, the cusps. So there are the angles appeared here. So there are no cusps anymore. There are these superattracting fixed points, four superattracting fixed points. One of them is put here, but it's better to think that it's at infinity. So we have four immediate basins for these fixed points. And we can ask ourselves, so whether we can perform the inverse procedure, inverse surgery from this map, given this map. So if we already know that this map exists for some reason, for instance, for the reasons that I have given you before, but there could be some other ways to construct this map, whether we can perform a David procedure and come back to the group. And there is a very sort of natural way of doing that. Namely, what one can do is the following. One can consider the so-called TIFR graph of this map, take the superattracting fixed points, and connect them by the arcs through the repelling points. And so you obtain the tessellation. It will be a tetrahedron tessellation of the sphere. And then take some face of this tessellation and replace this face by the topological disk. The topological disk by just blowing up. So that is this blowing up construction of this fixed point. So the faces will be replaced by topological disks. And in these disks, so we can now, so the original map, so in the faces of our tessellations would be kind of reflection of this face to the complement of the sphere, to the complement of this face on the sphere. And now we can, instead of this reflection, we can take just an actual reflection in this topological distance. So we have four topological disks and four reflections in this topological disks, which replaced the original rational maps. And then, and then we can construct and then we can do this in such a way that this map will preserve certain David conformal structure and realize this map as a piecewise Möbius map by straightening this David conformal structure. So that would be the inverse surgery from the hyperbolic map to the Kleinian group through the David extension theorem. Well, you see that it is an example. That is something that I already alluded to. So that we have a map and a group, Apollonian group, classical Apollonian group, and a map, which are really related in a very tight way. The Julia sets are homeomorphic by David surgery, and this David map is equivalent with respect to the dynamics. On the one hand, we have dynamics of the rational map. On the other hand, we have the dynamics of the Nielsen map, which is induced by the group, is generated by four Möbius transformations. So this example can be extended, can be just generalized to quite different than now general statement about relations between groups and maps. So this formulation is due to Russell Lodge, Yushan Lua, and Sabya. And the statement is that there is a natural one-to-one correspondence between circle kissing groups with connected limit sets. Circle kissing groups means that you just take the bunch of circles, so circle packing, which are tangent, and form some connected subset. And we also want the dual graph not to have cut points, so that the dynamics generated by the corresponding reflections will have the limit set, will have connected limit set. So it is on one side, we have this kissing circle groups. And on the other side of our dictionary, we will have critically fixed anti-rational maps. And there is one-to-one correspondence between this class of maps, this class of groups, and this class of maps. And this correspondence in one direction can be performed by means of the David surgery. And it is very, very similar to what I have just described to you for the example of the Apollonian gasket. So if you start with the map, so critically fixed map, so you take its Tischler graph, so the graph which connects the fixed points through the Julia sets, through the field Julia, through the Julia. Well, I should not say that. So we'll connect, so inside of the immediate basins through the touching point of this touching points of this immediate basin. So there is a Tischler graph. So then is each face of this Tischler graph by the topological disk, slightly smaller topological disk, and consider the topological reflections. So in this, with respect to this topological disk, and then you can do this in such a way that it preserves the David conformal structure, straightens this David conformal structure, and you obtain a circle packing which generates Kleinian groups, kissing reflection Kleinian group. So this homeomorphic Julia set, equivalently homeomorphic Julia set. So there is this, so kind of line in the Fatou-Salomon dictionary, which makes really explicit connection between these objects, Julia sets and limit sets. Now, so correspond each one to another in this very, very explicit, precise way. Okay, so immediate basins will touch independent points here. Yes. On the common points of the immediate basins. Yeah, disk touch it. So it is the boundary points here. It is the boundary points. We shrink the faces a little bit to topological disks, but they touch our faces in these repelling points. So like in the case of the gasket. So you see here is a face, and here is our disk. That is a touching point. Touching point between this basin and that basin. Okay, so here is another occasion of this kind of relations. Nice example. That is the example of the Julia set, which can be called the Julia set because it was exactly the one which was studied by Julia. So I would say that it is his main contribution to holomorphic dynamics, that he considered this example and really kind of tried to understand the structure of this Julia set. So it is a cubic Julia set, critically fixed, so that is its fixed points. And so we will perform this blow up surgery on all fixed points. So on these two fixed points and also at the point at infinity, replacing this fixed trace with the disks, and then so we can perform this David surgery and come up with which can be called the Julia group. So you see Julia group with a limit set. So the group will be generated by 4 reflections in these disks, so which correspond to our topological disks here. These 4 reflections produce this Julia set, which is canonically homeomorphic to the Julia set. This limit set, which is canonically homeomorphic to the Julia set to the Julia set. So, and it is an example of the so-called necklace group. Necklace group. It is an example of a kissing reflection group. It's a particular case of kissing reflection group, such that all these disks, they form a cycle of disks which on the boundary of one lie on the boundary of one domain. So there is this unbounded domain, and all these disks belong to the boundary of bounded domain. So that is what necklace groups. And particular case of our relation is the relation between necklace groups and polynomials, and critically fixed polynomials. So there is one-to-one correspondence between necklace groups, particular case of the Kiss and reflection groups, and critically fixed polynomials. And so, and again, it is equivalent on the Julia set by means of the David map. So it is just restriction, particular case of the previous theorem in the reduced to the necklace groups. Okay, so let me give you some analytic application right away. It is to the problem which is quite popular among analysts, so problem of removability of certain fractal sets. So removability means that if you have, so you have some fractal set, and if you have a homeomorphism, say, of the sphere, which is conformal outside of this set, then it should be a Möbius map. That is the meaning of removability. That is an important property, so and popular among analysts, as I mentioned. And we have, so of course, the most natural objects to test this property are dynamical objects. And this property was tested on the Julia set. So it is the work of Carlisson and John Sekos from the 90s, who showed that if we have a post-critically finite polynomial, the theorem is more general. Post-critical non-recurrent polynomial would be good enough. But so if we have a post-critically finite polynomial, I guess I don't need to say with connected Julia set, then this Julia set of this polynomial is removable. Namely, they actually showed that the complement, that the basin of infinity in this situation is a so-called John domain. John domain, without giving precise definition, it is domains which don't have cusps. Cusps are not allowed for John domains. And it is the right intuitive definition of what John domain is. And it is known, so by the theorem of Jones and Smirnov, that the boundaries of John domains are removable. And on the other hand, Carlisson, Jones, and Yakos showed that for this class of polynomials, for post-critically finite polynomials, the basin of infinity is John, and so the Julia set is removable. So in particular, so if we take this necklace group, for instance, this necklace group, well, not this necklace group, this Julia set, the Julia set, then it is a removable set according to that theory. However, for the necklace group, it was not known that whether it is removable or not. So in particular, Chris Bishop was interested in that question, and somehow he did not know how to prove it. But from the results that I have just formulated, it follows. So it is, in this situation, the limit set of our necklace group is the image of the Julia set under the David map. And we have a theorem which allows to conclude as a result that, well, it is a little bit more special result. But if we have the boundary of the John domain, and if we apply to the boundary of the John domain the David map, then in the image we will obtain a removable set. So in particular, so if we take any necklace group, then the limit set of this necklace group through our surgery and through this result of Carlisson, Jones, and Yakos will be removable sets. So it is some new class of removable sets is coming out from this discussion in a natural way. That is another kind of nice example. It's actually a rational map. So all previous discussion was about anti-holomorphic maps, so holomorphic of Z bar. So, but it is actually a rational map. So it is the mating of two parabolic Blaschke products. So there is a parabolic point whose basin is this pointer, is the symbol of this conference. So, but now I will tell you what is that. So you have this parabolic basin for this parabolic point, and you have another parabolic point, so for which the basin is exterior. And so, because of that, we have cusps in both directions, from outside and from inside. So we have inside and outside and inside cusps. So it is not a joint domain, so the complements, neither complementary component of this Julia set is a joint domain because there are cusps in both directions. So we cannot apply the previous theorem to conclude that it is removable. It turns out, however, that this curve, this Julia set, so is removable indeed. And here is an explanation. So explanation of this pine tree. So we have the two parabolic maps. So well, we have two parabolic maps. One of them has parabolic point here. Another one has parabolic point there. And so they conjugate on the circle, but this conjugacy does not match the parabolic point and does not move hyperbolic points to parabolic points. So we cannot directly apply our David extension theorem. However, so it can be done by taking the common uniformization of these parabolic maps by the z cubed map, by the tripling map on the circle, and then this map, according to our extension theorem, now we have a map which turns hyperbolic to parabolic, but not parabolic. So this map is David in this direction. So it emits a David extension to this direction. So here we obtain a David conformal structure inside of the disk. Similarly, we can uniformize the exterior conjugating z cubed to this map and pull back the natural structure, and we obtain a David conformal structure outside. Together, of course, if we have inside and outside David conditions, then we have David condition on the whole Riemann sphere, so we can straighten this conformal structure, and we will obtain our pine tree picture. So, and now by removing it, so we apply the David map to the circle. So the image of the circle under the David map is a removable curve. So it is a kind of a proof that the pine tree, which has cusps on both sides, this pine tree is actually a removable set. Okay, and here is another beautiful picture. So it is the Sabya's picture. So all the pictures here are produced either by Lee, so Nick Makarov's collaborator, or by Sabya. This is Sabya's picture of the hybrid Apollonian object. So you see, so we saw Apollonian gasket, classical for Kleinian groups, and we saw Apollonian Julia set. So, and in order to, so if we take the Apollonian Julia set, and on each of the four immediate basins, replace the dynamics of z bar squared by the triangular group, then we obtain an Apollonian group. And so what Sabya did, he replaced did this replacement just on three of the basins. He did not touch the basin of infinity. On the basin of infinity, we still have dynamics of the type z bar squared. But here, on three basins of these fixed points, he replaced the dynamics by the triangular group dynamics and obtained a hybrid object. And this hybrid object, so you see the features, there are these blue features of the group, and there are yellow features of the map. So it is some kind of mating between the group and the map. So quite non-trivial mating. And it turns out, it's not very difficult to show, that this dynamics is generated by two Schwarz reflections. Dynamics that produces this set generated by two Schwarz reflections. One of them is a reflection in the complement of our deltoid. Here you will see deltoid. So it is not circles, it's not arcs of the circle anymore, but it is actually the arcs of the deltoid. And inside we have an inscribed circle. So if we consider the dynamics generated by the Schwarz reflection in the complement of this deltoid and on this circle, then that is the object that you produce, and it is some hybrid object between Apollonian Julia set and Apollonian limit set. So, and it turns out that it can be done in many under many circumstances, this kind of surgery can be performed. For instance, here is the dynamics produced by two Schwarz reflections. So here we have a cardioid. Now it is interior of the cardioid. I mentioned that the interior of the cardioid is a quadrature domain, so we can consider the reflection in this cardioid, Schwarz reflection in the cardioid. And we have a touching disk, a disk touching to this cardioid. So we can consider reflection with respect to this disk, and we consider these two maps together as one dynamical system, and can wonder what we will obtain in this way. And you see that on this picture it looks pretty much like basilica, so or anti-basilica. So what happens that we can take basilica, or anti-basilica, we can take anti-basilica, blow up point at infinity, and when we blow up point at infinity, we replace these fixed rays. There are three fixed rays here, and we replace with this arcs, with this geodesic arcs, and then we will obtain this picture. So this picture is so it can be obtained by the surgery, by the David surgery, from the anti-basilica picture. So z bar squared -1. So take z bar squared -1. Do this surgery at infinity. So do this surgery at infinity, replacing the map by the group. Yeah, so we are performing this also partial surgery. So we don't touch the Julia set, but on the basin of infinity, we replace the map with the group. It will be again our favorite triangular group, and we will obtain a Schwarz reflection in the circle and the cardioid, which generate a mating between the basilica and the triangle group, the triangle modular group. And there is a general theorem. By now we have a quite general theorem about this kind of matings, that indeed any postcritically finite anti-polynomial can be mated with any necklace reflection group. So, and as long as there is no topological abstraction for doing so. So, and again, it can be done. By means of the David surgery. So there is this general mating result, and our reflection in circle and cardioid is a particular case of this result. It is another beautiful, Sabya's beautiful picture of a mating. So here you have the Julia set, which is a tuning of the Julia set by basilica. It is one half of the picture, actually. I think that it's a tuning of the Julia set of the basilica. And outside, you have the Julia necklace group. And it is a mating between these two objects. It exists by the general theorem, and it is a picture of what we will see. Okay, so you see, so we obtained, so this David machinery allowed us to do these two general results, this passage from the kissing groups to critically fixed polynomials and back, and also mating of necklace groups with postcritically finite polynomials. But there is a deficiency, some deficiency in the hybrid, in the David machinery, because it is not good in general for general non-hyperbolic polynomials. So it is not very good to check this David condition. So you usually need some sufficiently strong hyperbolicity. So you take the conformal structure somewhere, you start to spread this conformal structure around, and you need to control the area where the dilatation is big. So to do this control, you need something like postcritically finite, or maybe Colloquium, though it could be already difficult for Colloquium case. And so the previous results were about postcritically finite maps. But once you have some relation between the postcritically finite objects, after that you may try to to pass to limits and produce more general relation between already general objects, and in particular some connection, some combinatorial connection between the corresponding bifurcation loci. And I would like to formulate you a result in this direction. I probably should say that it is work in progress because it has not been yet released, a joint work with Sabya and Yushan Luo. So, and it is quite general situation, so of type, of these CNC types, cardioid and circle type. We can consider a bunch of Schwarz or quadrature domains, so touching, so a tree of quadrature domains, touching in various points, and we can consider a map, so just which is a reflection map in each of these quadrature domains. So, but it is defined on the union of all these quadrature domains. So such a reflection maps, and we can take a look at can consider the exterior dynamics of this map. We want the exterior dynamics of this map to be like not triangle, but in this general case would be ideal polygonal group. Some ideal polygonal group you take as an ideal, and we suggest regular, just to be definite, regular D+1 ideal polygon in the hyperbolic plane, and so the dynamics will be the dynamics of the Nielsen map in this. So Nielsen map for this polygonal group. So we fix some combinatorial data, namely we fix combinatorics, or we fix the fixed ray portrait, so combinatorics of fixed rays, so of our polynomial, and then we can perform the surgery, so replacing the dynamics, the polynomial dynamics near in the basin of infinity by the Nielsen dynamics associated with this regular polygon. And then we obtain such a general statement that there is a bijection between combinatorial classes. So we obtain one-to-one correspondence between combinatorial classes of periodical repellent Schwarz reflections, as here, and combinatorial classes of periodical repellent polynomials of degree D. So take any periodical repellent polynomial of degree D, blow up point at infinity, replacing the dynamics Z bar to the D near infinity by the polygonal dynamics, polygonal Nielsen dynamics, and so you obtain a Schwarz reflection of this type, and they will be, so not necessarily postcritically finite. All we require at this moment is to have all periodic points repelling. So, well, the particular case of this situation is exactly the CNC family, circle and cardioid family. And if we consider the bifurcation locus for the circle and cardioid family, that is the bifurcation locus of the circle and cardioid family. And so the family comes from one parameter. It is one parameter family. So we have a cardioid and we start to move circle. So the circle is supposed to touch cardioid at some point, and we can select circle so in various ways, so with various radii and touching in various positions. So it will be complex one parameter family of maps, or maybe a real two parameter families of maps, better to say. So and we can produce its bifurcation. We can produce a bifurcation diagram. It turns out that this bifurcation diagram for this set is exactly combinatorially equivalent to the basilica limb of the tricone. And the tricone is the anti-holomorphic analog of the Mandelbrot set. So it's a bifurcation diagram for z bar squared plus c. So we cannot claim homeomorphism between this bifurcation diagram and this one, but there is a homeomorphism between the corresponding combinatorial models. If we shrink classes to points, then there will be a homeomorphism between these models. So, and that is particular case of that general theorem that I formulated actually was our first example that we worked out when we started to develop this theorem. So first approach was without David surgery, but David surgery turned out to be much more general and efficient approach. And the proof goes by starting with postcritically finite maps on which we can perform David surgery and then pass into combinatorial limits. It is one straightening theorem. And another straightening theorem, I have just a couple of minutes just to mention that there is a situation actually when the quasi-conformal surgery is allowed. Somehow, quasi-conformal surgery, we need parabolic points to match. So if parabolic points match, then it is a good indication that maybe we can do parabolic then we can do quasi-conformal straightening of one map to obtain another map. And here is the situation. We can take so a slice of parabolic Bears-like anti-rational maps. So what are those? So put parabolic points. It is so map of degree D, anti-rational map of degree D. So parabolic point at infinity. So parabolic basin should be connected and simply connected, and should contain a single critical point. And in anti-holomorphic situation, we should also normalize the height of this point. In anti-holomorphic situation, there is some extra invariant, which is the height of the critical point. It should be normalized. This is a technical issue. So let us consider somehow this class, this space of maps. So you see, we don't consider polynomials, but we consider parabolic rational maps. So super-attracting point at infinity is replaced by the parabolic point at infinity. And then we can perform a surgery on this map by replacing the dynamics at infinity by the anti-Hecke group dynamics. Anti-Hecke group dynamics, and in this way, we will obtain a mating between this kind of rational maps and anti-Hecke group and the anti-Hecke group. So what is this anti-Hecke group? That is a picture of the anti-Hecke group. So just take a, say, triangle, so more general ideal polygon. So regular, so the group generated by the reflections in the sides of this triangle plus the rotation of this triangle, or polygon more generally, that is what is called anti-Hecke group. Yes, so I don't have time, my time is up. Let me just mention that this surgery actually is performed in 2 steps. And the first step of the surgery is again to do mating between this rational map and some other map, which we call anti-fairy map, associated to this group action. It is just the quotient of the Nielsen map by the rotational symmetry. So we obtain certain map, which is called anti-rational map, and then we can perform a quasi-conformal mating between this anti-fairy map and our parabolic Blaschke product, and then can lift this anti-fairy map and this Schwarz. We obtain some Schwarz dynamics, and then the Schwarz dynamics should be lifted by appropriate polynomial to obtain a mating of the map with the Hecke group. So it is very rough outline. So it is just indication of some particular family on which this kind of surgery can be performed. So it is so-called Chebyshev family, and it is very similar to the family that has been studied by Sean Bullitt and Luna Lamanacha. So, and which was the subject of the conjectures by Bullitt and Penrose. So somehow this theory is quite similar and quite parallel anti-holomorphic version of what Bullitt, Penrose, Lamanaka have developed in the holomorphic situation. Now we actually trying to understand precise holomorphic version of the theorem, and it seems that it is possible and works as well as in the anti-holomorphic situation, though it is more subtle. Okay, so let me that is a picture of this correspondence that I mentioned in the special case of Chebyshev family. You see some order 3 symmetry, and there is order 2 symmetry, which is just reflection, and they together produce this anti-Hecke group outside, and it is mated with some polynomial. In this case, it will be just z bar squared. All right, that is the corresponding parameter plane which can be related to the tricone in a very now precise way. So there is actually a bijective relation, so discontinuous in general, but bijective relation between the parameter plane of these Schwarz reflections and the tricone. So it can be justified through this quasi-conformal surgery. And I usually finish these talks with these quotations. From Fatou, who envisioned this grand unification between two areas of holomorphic dynamics, between iteration theory and the theory of Kleinian groups, and he envisioned it under the cover of the algebraic correspondences. So that was his grand unification picture, but at that time there were only two forces in nature known. It was Kleinian groups and rational maps. And now we have the third force, which should be included in this unification theory. It is the dynamics of Schwarz reflections. So, and there is a very strong interaction between all these theories, as we can see, but it is also subject of further exploration. Okay.